Diese Konferenz wird nun aufgezeichnet.
Good afternoon, dear colleagues. Welcome to online presentation from Elena. My name is Elena Jarzynski. I am from Forschungszentrum Jülich. Today, I would like to present you the recent developments and updates of thermodynamic database for oxide-relevant systems. This work was performed together with our colleagues from JDT Technologies in the framework of a Hot Vegas project. Generally, the Hot Vegas project deals with the basic experiments and detailed study of high temperature gas gasification and gas screening processes. And several institutes like Technical University of Munich and Technical University of Freiburg and Forschungszentrum Jülich, as well as several companies, are involved in the project. We in Forschungszentrum Jülich, we focus on the basic experiments of investigation of thermodynamic properties and phase equilibria using different experimental techniques like DTA, XRD, etc. And also together with JDT Technologies, we're working on the thermodynamic oxide database. Last year, a lot of binary, ternary, and also high-order systems have been investigated, and a lot of the important of oxides are presented here in the traditional flower. Concerning database development, two main directions could be pointed. First of all, we try to consider all possible combination of oxides. And also we perform the update of our database to keep it consistency and reliability of our database. And also there are some new oxides, which is important for interaction, for example, slag and ceramic materials could be added in the database. Today, I would like to present you the several exemplary system containing titanium, vanadium, nickel, and phosphor oxides, and also one new component will be presented later on. So the system containing both alkalis, sodium, potassium with vanadium pentoxide has been already in details investigated and presented by last JDT meeting. So in the framework of this work, we have studied the binary system with potassium and sodium metavanidates, and also the ternary system has been embedded into a database, including the quasi-binary section, for example, between two vanadates. And now we would like to extend our database by addition of other oxides, for example, two valence oxide like calcium, magnesium, and zinc. So, and by this way, we would like to consider all ternary system containing calcium, magnesia, and zinc oxide, including the quasi-binary sections which joins the two metavanadate, potassium and the corresponding two valence cation. In this case, we have embedded several ternary compounds to the corresponding ternary systems, and also it was not necessary to add additional ternary species in the system, because the interaction between binary, it was enough to reproduce the equilibrium between solid and liquid phases. Considering ternary system using our optimized data set, we can calculate for ternary system, for example, or subsolidus equilibria showing us the coexisting phases in the ternary system with zinc, and also for magnesia and calcium, we can calculate the liquid surface equilibria for both ternary systems. Considering the new example containing sodium oxide, we would like to add calcium in the system. In that case, the several new compounds, ternary compounds, have been integrated into the database in order to reproduce properly the subsolidus equilibria in accordance with literature data, as you can see here on the slide. And also, extending our database, we are able to calculate the liquid surface for the ternary system, where the primary crystallization tilts of the several oxides have been marked by different colors. Next system contains iron. In that case, we consider iron-free, iron in equilibrium in air, and all binary system between corresponding oxides have been already done using that database, and all binary vanadates have been included into the database. And now we would like to consider the ternary system. First of all, we have added the two ternary vanadates, which are located on the section between sodium vanadates and iron vanadates. to reproduce the subsolidus equilibria in accordance with literature, with available literature data. And also to look at the equilibria between solid and liquid phases, we can calculate this quasi-binary phase diagram joining iron and sodium vanadates. As you can see here, both incongruent melting compounds have been shown on this figure in accordance with experimental data. So the next two valence cation which was considered for sodium vanadates was zinc oxide. And as usually, in most of cases, we have only data about the subsolidus equilibria. In that case, in the system exists only one ternary compound which was calculated to melt congruently at 600 degrees C. And using this information, later on we can calculate the completely liquid surface of the ternary system containing zinc oxide. So as I said in the beginning of my presentation, we try to consider all possible combination of oxides, and also we try to update our database. Therefore, this slide shows us the example of reconsideration or reassessment in our database. In the system alumina vanadium pentoxide, this system has been investigated based on the experimental formation of phase diagram information from Tombe literature. Later on, some new experimental information have been found, namely thermodynamic information about the aluminum vanadate, including CP measurements, also adiabatic colorimetry for low temperature range, and also some new phase diagram data. And therefore, all this information should be elaborated, should be included into a database. So therefore, we need to update our thermodynamic description for this system. All this information, thermodynamic for aluminum vanadate and phase diagram, have been used later on for reassessment of this system. And in the end, we're able to reproduce quite good for example, CP function for aluminum vanadate, including the low temperature interval based on the adiabatic colorimetric information. And also we're able to calculate the phase equilibria for this binary system in very good agreement with available experimental information. So the next example concern the example so-called coupling between experimental and modeling research. As I said, in our group, we can perform thermodynamic investigation, experimental thermodynamic investigation of oxide system, because sometimes we don't have enough experimental information for complex systems. It was the case of nickel oxide and phosphor pentoxide. Using DTR and DSC technique, we have measured the thermodynamic properties of nickel phosphate. For example, the heat capacity has been measured from low temperature to the melting point for nickel metaphosphate, and in combination with literature data, we can reproduce quite well the thermodynamic function for nickel phosphate, and also by using this information together with literature data, we can use this information directly in the assessment. So, and in the end, we can reproduce very well for example, phase equilibria for this binary system, as you can see here on the right side, including literature data also. And for example, reproduce with a good agreement with reference the enthalpy of formation for different nickel phosphates. So by extending our database, we would like to add alkalis to the binary system phosphor pentoxide nickel oxide. For example, in case of sodium, we have experimental information for two quasi-binary sections. One of these joined the two metaphosphate. In that case, we have one incongruent melting compound, which was modeled in order to describe properly the phase diagram for this section. And the next section contains both stoichiometric compounds and solid solubility based on the high temperature modification of sodium octaphosphate. Actually, we have already this phase. Before we have considered the solubility between sodium or potassium orthophosphates with other divalent cations like calcium, magnesium, or zinc. And now we try to add nickel oxide in this, using the same phase description in order to reproduce the solubility between sodium octophosphate and nickel octophosphate on the other side. So looking at potassium containing system, actually we would expect some similarity between two alkalis, but in this case we have only one quasi-binary section, which is located between two metaphosphates, and here we have two incongruent melting compounds which have been integrated into the database in order to reproduce the equilibrium between liquid and solid phases. And since no further experimental information about this system, we can extrapolate, we can calculate the ternary equilibria in the system, as you can see here by the liquid surface. Last topic which I would like to present today. As I said before, we need to introduce some new components in the system. And here, a lot of binary, ternary, and also high-order system with lithium oxide have been considered using the available experimental information from the literature. And some list of these phases you can see here on the slide. And also, lithium must be embedded, incorporated into the solubility phase in the liquid and solid solutions. And for many aspects, actually, lithium oxide should be very similar with other oxides or with other alkalis. For example, in the system lithium oxide, phosphor pentoxide, we have the same congruent melting phosphates, and the same phosphates are used as a species in the liquid phase. Similar has been done for sodium and potassium. For next system containing alumina, here we can see some different behavior, because in contrast to the potassium or sodium, for lithium containing system we have another compound on the lithium rich side. The second, the compound lithium aluminum 5 or 8 can form spinel phase with magnesium aluminum spinel. Therefore, we need to describe the spinel phase to provide the proper description for the spinel phase in order to reproduce this phase also in high order systems. And it has been done because we have already spinel phase in our database, and the lithium was incorporated in form of some special end member in order to keep the required stoichiometry. And using this description, we can predict the formation of spinel phase on the binary system, as you can see here, as a solubility area. And also, for example, for another binary system containing iron oxide. In that case, according to the literature, the solubility of the spinel phase extends up to 80% of lithium oxide. And therefore, we use the same phase description for spinel with addition of corresponding end member, and also considering the corresponding interaction parameters in the spinel phase. We're able to calculate to predict this solubility area for iron containing system, as you can see here on the calculated phase diagram. Looking to ternary system, for example, by addition of magnesium oxide to lithium oxide alumina, you can see here the spinel phase, which exists in the form of one phase between lithium aluminum side and also between magnesium aluminum spinel. And the corresponding end members are presented here below in the table. And also, in accordance with literature, we have incorporated the lithium also in MAO phase to provide some solubility, which has been reported in literature. So the next system we have, as third component, we have sodium oxide. And again, you can see here the spinel phase, which is end member, the final end member lithium aluminum 5 or 8. And next phases which should be described here is beta prime and beta alumina. Actually, for the system without lithium, these phases have been considered as stoichiometric compounds for sodium and aluminium. But now, to provide the solubility with lithium, as reported by Duncan, we need to add lithium into beta prime and beta alumina using the sublattice model, as you can see here on the table. And by this way, we can reproduce the coexisting phases spinel and also beta prime and beta alumina, as you can see here on the isothermal section at 1300 degrees C. And the last example contains silica as added to both alkali oxides. And here you can see, in addition to the liquid phase, which contains alkali oxides, silica, and also silicates. And all the silicates have the similar chemical formula to keep the consistency of the database. In addition to this phase, we need to describe also solid solubility in this system. And the sublattice model has been used to describe the solubility between corresponding disilicates, sodium and lithium, and also the same model actually was used to reproduce the solubility based on the metasilicates, the corresponding alkalis. Concluding my report, so in the framework of development database, we have considered several new combination of oxides in order to provide the completeness and reliability of our oxide database. And also the new component, lithium oxide, has been integrated into database, and a lot of binary, ternary, and one higher order system has been considered using the available experimental information from the literature. And also lithium has been included into the several liquid and solid phases. And the actual present state of our thermodynamic database you can see here on the table, including information about the amount of binary, ternary systems, and so how many select components we have at the moment in our liquid phase. And the last slide shows the continuous developing of our thermodynamic database, the updating and modification of our database. So thank you for your attention.